Hello, and welcome to the latest installment in our UXDX online series. I hope you're as excited as I am for the talks we have this evening. But before we jump into those, I want to give a really quick introduction to UXDX and why we host these sessions. So at UXDX, we say the world is full of bad software. And what I mean by that is not software that doesn't work or has bugs, but it's the usability of that software. And I always go to my banking example because I have a bank, a very traditional legacy bank, as well as one of the digital first banks. And the apps, while technically they do the same features, there's one that's 1,000,000 times easier to use. And so because of that, I do a lot more business with that bank. And our mission at UXDX is to help companies build an environment that can't build bad software. Because I don't think it's down to the people or the motivation or the skills or anything like that of the people in those companies. It's the environment and the processes that they're forced to use that ends up in these clunky and difficult products. And how we help companies make that transition is to move from waterfall, or more commonly water scrumfall projects, where everything's locked in months before and you don't have the ability to iterate and learn, to truly empowered autonomous product teams. And that's really easy to say, oh, it's a little change, but it involves changing absolutely everything around how you structure teams and how they work. Now, one talk is not going to cover that entire process, but we ask people to share how they're adopting the latest tools, the latest practices, the latest processes in their part of the process or in their kind of industry. And hopefully you can listen and learn from that and see how you could apply that in your context, kind of advance the way you're working. Now, hopefully as you're listening, you can start getting some questions about how could this apply for you. So please do write those questions in on whichever platform you're watching this on, and we'll put those questions through to our speakers. But that's enough about me. So I'd like to introduce our first speaker for this evening, Megha Sandesh, who's the CEO of Solvedex. And Megha will be talking about the resurgence of mechanical Turks, a primer for true AI-based automation. So I'd like to welcome Megha to the stage. Over to you.
Thank you so much for the introduction, Rory. So as mentioned, I will be talking about how we've kind of gone back into an age where we are resorting to use the equivalents of mechanical Turks in order to almost spoof or pretend like there's AI. And what is a true solution to include humans in the loop and to make sure that we're actually innovating with UX and product design and experience in order to actually build better systems. And through that, I'll also be talking about some practical examples that we've done at Solvedex, which ended up basically solving the problems of tech debt. So with that, let's get started. And this is our basic agenda. So I'll give you a quick introduction about some of the work that we've done at Solvedex and Solvex, and essentially what are the principles that we have set up in order to make sure that we are continuously designing for the human experience and the journey of the learnings along the way, as well as some practical examples in various industries. So what we do at Solvedex is that we are actually leaders in the fractional space. So I myself have worked as a fractional CTO and head of product for different companies. And through my work at the different partners, some of which you see here below, I have started off as a software engineer before moving into product and design, which has been my true passion all along. So during this work, I've also managed to set up a separate entity called Solvex, which is our design agency. So we work much like any other traditional agency in that we consult with startups and medium-sized businesses, sometimes large Fortune 500 companies as well. And we try to concentrate on one single problem that they're having. Sometimes that could be holistically the entire company's product experience itself, and really innovate to work really one-on-one with the company and the teams to make sure that at the end of it, we deliver a product that delights the users and also solves important problems for the business. So let us talk about how design systems for AI have evolved, because I think traditionally we've had design and we've moved into design ops. Right about the same time, ML ops came into usage in the modern parlance and practice, and this has also led to essentially a parallel evolution of AI-backed software development and essentially AI-generated products as we see now. But I seen through firsthand experience that we've not moved enough in the product and UX design space to actually create systems and components which are truly based for an AI created world, or products that involve AI but with a healthy dose of human interaction as well. So obviously we see now in product design that you can use basically AI generated content. You can also generate drafts of your workflows, even full-on wireframes from scratch, which get us about 90% of the way there. And I've never believed that those are really the problem to begin with, nor that they take the human out of the loop. It's more so that when it comes to basically use cases that involve a real problem where ChatGPT is not capable enough to help, then essentially humans end up picking up a lot of that brunt of the work. And what is supposed to be AI is simply not. So let's come back to the topic of design systems, because at a glance, they still remain more or less the same. So at the first level, you have things like your buttons, atomic designs, and basic components to make your program work. And most companies do not go beyond pattern libraries, pages, and a few other standards and so on. Because I truly believe that the real product innovation as well as the payoff comes from the strategy that you build around your evolution of the design system and keeping in focus the users that you actually design for, as well as knowing what is the end goal of your product, as well as keeping in mind that every product has an end state and there is an end of life. So effectively planning for that and executing that has been one of the ways in which I found the innovation to work better. And this is kind of where we've concentrated a lot of our work at Solvedex. So then let's talk about what is missing. So I've hinted to this before, but one of the problems that comes with the audience that we work with, which is small to medium sized startups, so think anywhere from 5 people to almost 250, they usually do not have a mature design team to actually man design systems and really take care of that. So you essentially end up building almost like an ad hoc design for the product to meet the goal at hand. And again, that leaves out the user, who's almost the last chain, but we all know that that's actually the most important person. And with the evolution of AI and machine learning, so I'm not just talking about LLMs, I'm also talking about traditional machine learning models, which truly take in a data set and learn user patterns over time, usages and behaviors, and actually help automate and cut down human effort. So when these kind of things are involved, it basically magnifies this negative effect. So we are increasingly designing for AI to talk with other ML and AI algorithms, and increasingly less in a way that essentially humans have to adapt their behavior in order to accommodate for this, and not the other way around. So we see a lot of artificial behaviors, which means that we're not able to actually create the business value and the ultimate effect. So you might end up designing something pretty and something that's fast, but maybe not something that's relevant and solves a real human problem. So then let us talk about some of the core principles for AI design and what constitutes a design delivery system that really shines and makes a difference. So we start off with some of the same principles that are applicable for any AI, which is transparency, things like progressive disclosure and giving the user back control so that things can be overridden to the effect that they should achieve, and being able to adapt and build in feedback loops, right? So as you can see, it's on the screen, but I'll be going through some of them in detail. And once again, putting the human back into the focus is the biggest concern with this one, because as I mentioned, like with the reemergence of mechanical Turks, so for those of you who don't know what the mechanical Turk is, it is an old centuries-based machine which was presented to others as a machine that was intelligent enough to play chess on its own, but internally it was just a man operating levers to move pieces on the chessboard. And we see that more and more, most products have to use the word AI in them, even if there is no component of AI. And essentially, it boils down to badly paid humans who are doing most of the work manually and serving up as the result of the AI. Now, of course, with LLMs, they've evolved to a point where they're actually useful, and we have seen enough of generative and agentic AI. But there are still use cases and complex systems which are nonetheless extremely relevant, who require a higher level of effort in order to make sure that we're truly making a difference. And these are the cases where, simply speaking, the aspect or the fact that we use humans to what should be doing machine work is simply not acceptable. And as I mentioned before, we design for machines, and yet we let humans use them in a way that makes everything inefficient. And that's, once again, it takes the human out of the focus, and somehow we keep the human in the loop, and it's never the same. So let's talk about a few case studies that I worked on to make sure that we could actually put the human back in the loop, in the focus, and then design for true automation, as we mentioned. So one of the case studies where I was heavily involved in is a product that I did for one of my partners, which involves contractor management. So think about it like almost like Uber for home repair contractors. So if somebody has a leaky roof or requires a repair to their door, then you call up a contractor who basically visits the site, understands the issue, performs and creates what is called a field bid, which is an estimate of the repairs and the cost and so on. And so as you can see, there's a lot of steps involved where the contractor has to do a site visit, perform an estimate, then somebody else in the back office has to actually approve of that bid and going back and forth with the final homeowner to make sure that they are confirming that they want to go ahead with the repair. And the other parts that make the system inefficient, or shall we say that ripe for automation and innovation, are the fact that each county in the United States, each state has a different level of permitting, different requirements to do the same repair, and perhaps even the skill level of the contractor involved to make sure that they can fully perform these repairs. So essentially, this is where we trained a mixture of different AIs. So it was a mixture of an LLM as well as a homegrown machine learning system, which was trained for this specific use case to make sure that it could learn of how to automate things like getting permits, creating invoices, creating accurate bids, and making sure that we can actually truly automate this. So as you can see, I think it should be pretty clear that there's no automating your human work that has to be performing the repair. But what we were able to do successfully is that we allowed for contractors to make bids by things like human dictation, text to voice to text interfaces, and then that was all input into an LLM, which is again an actual remix of ChatGPT, which was then able to spit out standardized bids, which all came in close to the same level. So one of the biggest achievements of this was consistent repair estimates. So therefore, even if two contractors visit two different sites, if they're of the same repair estimates, then we made sure that they're coming in with around the same range, if not the exact same amount, if it's the same repair, which was a problem that the system was having. And then the other big innovation was that we automated the entire process of permitting in certain counties and certain states. And this became even easier, especially where one contractor was servicing different states. So for examples included, if somebody was in the state of Mississippi and they could go back and forth to Louisiana or even Alabama or sometimes Florida, so they could actually service different states, but make sure that they got their same permits on time and save a lot of human headache and effort in the process. And going to the next one, here are some other screenshots of that system in action. As you can see, it is a ChatGPT prompt, which allowed people to actually generate consistent bids, came in at the same pricing. So that means satisfied homeowners, satisfied contractors as well, because they got paid on time for repairs that they did fast and efficient. So overall, a huge win for the system. So then let's come back to the topic and talk about what a design delivery system constitutes in this case, using this as an example. So we know that, while the ultimate goal of all of this is full automation, we understand that we're quite far off in most cases from achieving that. And that's despite having all of the available off-the-shelf applications and help that we can get from AI systems. And basically, we also know that not all systems will be ever fully automated. Again, going back to the example of human repairs, they will still remain human repairs until we can actually get machines which are so well evolved that they can also perform the repairs. So we know that within the bounds of this problem, there's not full automation in whatever sense that we choose. So we design for progressive automation, and we work on that. So that means that all the components that we do in the design system have to involve the fact that they are at a certain level of automation now, but we are looking forward to progressively automating more and more. And it's not to put the human out of the loop. It's simply acknowledging the fact that the system becomes more efficient. So it should not be held back by the UI and the experience in order to do that. And basically, by closing the need for what the customer truly desires, versus what is actually delivered by the contractor, in this case, by the system, by the back office staff, we make sure that we can achieve the results faster, and we can, more importantly, reduce unnecessary human effort and legwork by automating out repetitive tasks, by automating things that can be taken care of by computers. So in this case, things like permitting that does not require a human. So in this case, one of the biggest achievements was that more contractors were actually brought into the platform, and basically creating more jobs in the process. And it did not make any of the back office staff redundant. Instead, it made them more efficient because they were servicing more number of jobs, but at a faster rate. Therefore, everybody saw growth all across the board. And I think that's one of the facets in which we have to use AI to make sure that people are becoming efficient, not redundant. So for my next case study, this involves a system that we did for grocery shopping. So you might have seen some of these analogous or similar systems before. So Amazon had what they call just walk out systems. So basically you walk into one of the Amazon stores, not necessarily Whole Foods, but this was like one of their specific stores where they've set up cameras and other systems where they're continuously watching and recording every single shopper that walks into the store. So the shopper can then walk around freely and pick up items that they want to purchase on that day. And then once they're done, they simply have to just scan in a QR code and they're ready to walk out. So it's what is called a checkout free system. So I was involved in building basically the biggest competitor to the Amazon system. And one of the biggest changes that this system allowed for is the fact that unlike an Amazon store, there was a whole lot of different actions that we knew that the humans would do. And we basically coded into the system. So things like, we know that, for example, well, people don't necessarily just do grocery shopping by themselves. They also bring in family members. So we allowed for multiple family members, up to 8, to be all recorded and monitored at the same time. And when we think about a grocery trip, you can break it down into different components that you're either picking up items or you're putting down items, and then you're also doing things like weighing items which do not have a standard weight. So, a packet of Lay's chips is always almost the same weight, and what are the different weight classes. Whereas a packet of meat will be almost always having different weights. So you have to account for those things. And that's what the system did. So instead of putting the pressure on the user to adapt to the system instead learned from human actions. So there was a feedback loop that was built in, and this is the one of the interfaces that allows for, again, humans in the loop in this case, who are called quality trainers, who can then correct the system and correctly identify products when required. So within the years that we were involved in the building and the evolution of the system, we created this design delivery system where we know that each component has a certain level of automation. So the things that I'm showing you here take into account the fact that certain components, things like a card, will initially be seen by a human, but will be automated away. So how does the system look like when it's automated? So when we need to give in that feedback loop, when we are at an evolved point in time, we can always come back. But we plan for the level of automation and we plan for the level of precision that's present today, knowing that the system is being trained and the system gets better over time, and the UI enables that and then adapts to that. Because the UI here is not just to service the status quo and to just simply enable the workflow. It is also enabling the improvement of the system. So when the system improves, the UI gets left behind. And that's kind of where we come in and say, great, now let's make sure that the UI is now ahead of the system so that it can service the level, and then it can also accommodate for where the system needs to go next and become more precise, more exact. And once again, not take the human out of the loop, but make humans more efficient. Now, of course, with the system, the goal is to take the human out of the loop and to not have quality trainers. Maybe have a quality manager that can come in and do occasional fixes. But that means that those quality trainers will have transitioned to a different spot in the system that requires that evolution. So there is always a plan for obsolescence, for the end of life and things like that. So then let us talk about one of the unexpected benefits that we started seeing through first like this, because often we don't talk in the realm of tech debt when we're considering product and UX design. But again and again, working through, especially in industries like healthcare and enterprise systems, I see that as systems evolve, UI and UX designs and releases in some way contribute to the accumulation of tech debt. And it's due to the fact that the UI gets left behind and the user experience is a little previous generation compared to where the actual technical systems. So work with ML scientists who designed better and better algorithms through the data and the training sets they were able to accumulate, so that the system was doing things faster. The system was being more precise, less false positives and false negatives and so on. And yet the user experience remains static, kind of almost trapped in the components and as I mentioned to you, the level 1 and level 2 of the components that we design, not taking into account the fact that the user has evolved and become better and the system has done the same thing. And yet the experience often becomes the bad link in the chain that lets them down. So then when modular systems take into account the level 3 and level 4 of what I illustrated, which is that we know that the system will get left behind. And so therefore we upgrade the user experience because we've already built that into the design system. So now we're actually delivering that experience, which not only keeps up with the user and the system, but actually outpaces it so that it can really guide the system and the evolution in a way. And that then basically gets rid of a lot of the tech that's accumulated. So whether it's through implementing a new system, a new backend, or a new API, it also leaves behind a lot of the debt that accumulates in the user experience due to using old patterns. Because the fact that evolution is built into the pattern basically makes it possible that we can swap out whether it's individual components or entire patterns without a disruption in the experience, and it just becomes a regular part of the evolution of the system. So I'm coming to the conclusion of my talk, and I would like to leave you with a few key ideas, which is that we've always known that user experience should evolve, but we've often thought of it in generations or redesigns, with much of the UI remaining same and the UX therefore lagging behind for most of a system's lifetime. I think it's time to move away from that and really start embracing this level of adaptability, because we have to realize that we are not designing products for AI, but we design products for humans by putting them in the focus and not just in the loop, in a world that has AI and that is enhanced by AI. And that's the world that we actually want to build. And that's done through transparency, progressive disclosure, and giving back user control. So, as much as we would like automation, we have to realize that we sometimes have to be vulnerable and actually give back user control, because when the user feels in control is when they can actually achieve their goals. And that's really the end goal of every business, is to solve relevant problems, not just to solve a problem faster because they can. And let us also be mindful and progressive in how we measure the success, by once again keeping the humans at the center, and and being holistic about what kind of problems that we are solving. And I believe that this kind of design delivery system will actually lead to better automation, knowing that we are solving human problems, and by actually starting small and thinking about the progress of it, so that we are always learning and failing, but knowing that the system and therefore the user experience can actually show the better way forward, and we always know where we're going is in a positive trajectory. And as you saw through the case studies, this is possible for small and medium-sized startups and not just large organizations to evolve into. And I see actually a very, very positive way forward if we were to adapt this. So with that, I will now conclude my presentation, and thank you for your time. And I will be taking any questions that you might have.
Excellent. Thank you very much, Megha. That was some great examples of kind of some of the ways that we can start looking at adapting and using AI in our products. I want to launch with a first question, because one of the biggest challenges that I've seen is, I guess, there's hallucinations, there's the unpredictability. So you mentioned in your first case study about permits, and it was helping to do that. Is there a risk there? I think there was an example with an airline where the AI started giving out refunds or something along those lines. Is there a risk that there's some hallucinations and you think you're legal for some jurisdiction, but you end up not being? And how did you solve that kind of risk?
Absolutely. That's a great question to start off with. So this is kind of where the concept of the feedback system really comes into play. And I have to, kind of point out that when I mention a feedback system, I'm not just referring to a little form that we use to submit feedback. Sometimes feedback systems can be that, but sometimes it's a full human override where, if required, you can completely ignore what the AI has input, and you need to do something yourself. So that then becomes kind of an idealized training set for the AI to learn from as to what it is supposed to output, right? The second aspect of it is to kind of set the boundaries very carefully. So we know that, for example, if the repair requires only one roof, then the permit does not ask for three of them, because that's the kind of hallucinations that we see. And if we require to replace n number of components, then they shouldn't be a different number. So and the other aspect that I touched upon with the specific example of the contractor management was that we also know price bands. So there you have to build these systems and checks and balances in place, so that it's not just one check, but it's multiple checks. And finally, that also passes through the human inspection. So again, as I said, we're not taking the human out of it. There's always a human check at the end of it. But now they can actually do it better, because they're not spending about 3 hours just creating that permit. Now they're spending about 30 minutes waiting for it, so that then they can spend that last 10 minutes making sure that everything is in place. So absolutely, feedback systems, boundaries, and final human intervention in a way that's actually usable, and does not try to just fit or retrofit what the AI has done into something that is more acceptable, is the way forward. Because as I said, sometimes the AI will input something that's just complete nonsense. Most of the time you start with that process. So it is up to us to train the AI. So it's almost like training. It was a little bit like training kids. It's better to start with good habits first and train one good habit at a time rather than start and correct 20 bad ones.
Brilliant. That's great. I'm just looking. I think that actually brings us up to time. So we've only got a few seconds left. I just want to thank you once again, Megha, for sharing. I thought that was a brilliant kind of answer as well, particularly because I know I'm guilty of trying to get AI to do a big task. So just break it down into those small little chunks and course correct at each step of the way is a great piece of advice.
Thank you.
Thank you very much. Okay, so that brings us to our second talk of today, which is Pritam Roy, who's a senior manager at Capgemini. And Pritam will be talking about AI-driven innovation, transforming retail and fleet management for the future. So I'd like to welcome Pritam to the stage. Over to you, Pritam.
Thank you so much for this introduction. To give a brief about me, I have around 20 years experience working in this industry. And today I will talk about the usage of AI and machine learning in fleet management. The fleet management industry is always evolving. Back in 2019, there was a paper published by Volvo on how they can capture the telemetrics to improve the working of the machines. Till then, different industries in logistics and transportation took those learnings and from research papers and started to evolve, utilizing the fleet management system into their company. The transportation and logistic companies with integration of AI in fleet management opened a new possibility in this era. The business is supposed to increase from 8.1 billion currently to 19.5 billion by 2032 by the usage of AI technologies. The highlights being use of machine learning, LOT, and cloud computing devices to enable predictive maintenance and intelligent routing optimization. Think that most of the people today, we use Google Maps to travel from one place to another. What if these things are used by a driver to deliver a product to a store? Suppose a store sends an SOS that they're running out of stocks for a specific product during a promotion time or during our season time. A driver can plan his route, he can predict by when he will reach, and that way that one can be fulfilled by the customer, end customer, by the company, or by the end store. So it really opened new possibilities. Stores can share their warehouses with different customers, different kind of people, and that's route planning make all these things possible. To summarize, like how we can use AI in fleet management, let divide it into few compressive steps. One is predictive maintenance, where AI systems can forecast vehicle failures with up to 90% accuracy, reducing breakdowns and maintenance of cost significantly. Imagine a vehicle which is going to break, and if we can predict that, it will save company a lot of money because they can go and fix that vehicle rather than having a vehicle driver calling them from the mid of a note at night that, okay, my vehicle had breakdown, I need a mechanic to be sent here, or my vehicle needs to be towed. So that helped companies a lot in predictive maintenance.
Sorry, Pritam, to jump in. I'm not sure if you're moving through slides, but we only have one slide on the screen. I'm not sure if that's correct, so apologies for the interruption.
I'm just giving an introduction. I will go to the slides here. I will explain the slides later. Yeah.
Apologies, I just wanted to make sure. Thank you.
Okay.
Sorry about
that. About fuel efficiency, this will definitely help in fuel efficiency because using AI, we can predict driver behavior, how much he uses his fuel in traffic. Future directions in this is that emerging technologies such as federated reinforcement of blockchains and EV-specific analytics can further enhance our system of data security and system fleet maintenance. Now let's look at the diagram here, how we can capture the data that can be utilized for the maintenance. Imagine in the left side of the diagram, we have a driver which have a telemetry device installed in his vehicle, which will send data to different data providers. We will have different telemetric polars that will be capturing the data. from different streams, we can route that to Kafka. We're using Kafka as a data stream because it is very fast. It can support around 100K streams per second, and we can route that to different databases, which can be in memory or which can be fast databases like Kinetica, maybe a MemSQL, which can aggregate the data in real time and create some dashboards which can be controlled by a provider who will sit in his office to see, okay, where is my truck? What's my location? Is there any storm that is coming? Can I suggest a driver an optimized route to reach a destination? Apart from that, it will also send that office a remote diagnostic of the vehicle, how my vehicle is performing at this location. Do I see any issues? Do I see any issues in the brake or the tires? Do I need to ask the driver to stop at a certain point so that I can fix the issue? That will come from the operations hub. Apart from that, once a day have passed, that the data can be sent to an analytics hub where data scientists can use the data to see how that the driver behaved during driving. Did he drive fast when there was a speed limit? Or is he using a different route than the planned route that is delaying my delivery? So all these things can be captured in this fleet management for better user behavior and better for the company. Let's look at the conceptual model. What we can do. Suppose there is a provider which leases his vehicle. So when we lease a vehicle, there are certain steps in that vehicle steps. One is that we go for agreement. We can buy certain products that vehicle get attached to a supplier for certain time period, and we also enter the agreement with certain customers. All this can be controlled in this data model flow. The data will be in one location that can be used for predictive maintenance. In a real-time architecture, how it will look. There are certain external data providers which will send us the data. We have Zoner. We all know about it. We have Samsara. That also is a provider. Verizon Connect, Cortex, Geotab, Trimble, Omnitrax. All these providers today, they are sending data to different industry collecting from the vehicles. We will implement a device in a vehicle, maybe in our fuel tank, maybe we can put a sensor in the speedometer, maybe we can check the tire pressure by putting a device, maybe we can check a battery health, and the data will be pulled and sent to a Kafka topic. Different applications will have different topic. We will be having a reading application, which will be reading the data from different topics, and then using a data flow, any ETL tool, we can send the data to a data lake that will be stored for history purpose, into a data warehouse, which will be used for analytics purpose, into some geospatial temporary data set for near real time.
Pritam, I think we've lost your audio. It just dropped out there a second ago.
Am I good now?
It was working fine, but it just suddenly dropped out.
Can you hear me now? Can you hear me now?
I can't hear anything. Okay, Megha is saying it's a problem on my side. Apologies.
Oh, okay.
I'll drop.
Okay, so let's start again. I lost the track. So we have different external data providers which support us using the polling device like Zoner, Samsara, Verizon Connect, Cortex, Geotab, Trimble, Omnitrax, Volvo. We can pull all this data using a Kafka topic and send it to applications. Real-time applications will manage something as a spatial data like MemSQL, maybe a Kinetica. Data version can be sent to any Databricks, maybe a Snowflake, and we can have built data lake built over Azure or S3, which can be used for analytics purpose. There are certain tools in Amazon. Of course, our product is mainly in Amazon. So I mentioned Amazon Athena, Amazon SageMaker, which can be used for analytics purpose. All this data which we are sending from telemetrics, like the data from the battery, from the engine, from the fuel consumption, tire pressure, brake system, battery health, can be used by data scientists to predict whether my fleet is performing perfectly, whether they are following the proper route, whether there are any issues in the vehicle, and that can be used by the end users or by the company managers to predict what was my route optimization. In the next slide, I will talk about the APIs which we generally use in managing those vehicles. On the left side, I have a service called locate management, which will go and hit the API gateway to get the data and the real-time location of the vehicle, where my vehicle is located, how it is behaving, whether it's following the route. We can use the Markov analysis algorithm for it, where it will state whether what was the previous spot of my driver, what is the next spot of my driver, so that I can predict where my vehicle is going. And if I can get traffic data in real time, I can say how much time it will take to go to a warehouse. We can also have a vehicle finder API to locate the vehicle at a specific time, at a specific location. And if my vehicle gets stolen, this can be used possibly by different agencies, federal agencies, to locate my vehicle. That is a best use case these days. We see federal agencies locating a vehicle that is stolen in US. Apart from that, suppose a rental company is renting their vehicle, they can predict in real time where the vehicle was taken. If somebody is dealing in returning the vehicle, it can be tracked and we can get that vehicle without any difficulty. There will be an API that we have developed for proactive maintenance. Based on the pings, we can send an API request to the vehicle to ask it to return back to the nearest service center. The driver will see that in the dashboard, through which he can take corrective actions and return it to the nearest service center. All this can be managed at the backend in a different kind set of databases. I have mentioned geofencing, unit location, actual location, not reported unit location. This is something where the vehicle goes, which we have not planned. So we can store the database to warn the driver where he has gone out of the track or out of the road and taken the vehicle. Apart from that, we will have a dataset for UT current location, which will state the current location of the vehicle. Technologies that generally we use in this for CI/CD platform, we can use any general available technology. For better, currently we use Bamboo here for CI/CD. We have Bitbucket, we have Maven, we use Flyway, we have Jira. For deployment, use Amazon EKS, or we use different in-house libraries. For UIs, we use Spring Boot and Spring Security. For containers, generally we use a Docker container here. Streaming, I already mentioned, we use the Confluent Kafka topic for streaming purpose. Analytics, it's a big ball game. We use Amazon EMR, Amazon Ethna, Amazon SageMaker, Amazon QuickSight. Data IQ also is evolving. There are certain cases where we can use data IQ for prediction purpose. Observability, generally we use Wavefront, we use and Logstacks. What we do when we get the logs from different vehicles, we try to apply analytics to see whether all my components which I'm using for prediction are working properly or not. We use PagerDuty and SMS modifications to send real-time messages to the driver. So in short, with this kind of applications, what we have done is that we have revolutionized the fleet industry. Today, in real time, we can know where is my vehicle. I can plan my fleet, which route it can go. Apart from that, I can predict the shortage of my warehouses and route my vehicle according to that place. To talk more about optimization, there will always be a high initial investment. Generally, industries these days, they don't want to invest first more on this. because the cost of sensors, infrastructure, AI platforms can be significant. Imagine that if we are putting an LLM to predict all this data set. It will be a huge data set running few GPU servers, and it will require significant investment and ethics cost for that. Whether a company is interested in doing so, it initially is a challenge. But in long term, this generally helps significantly for the industry to maintain a fleet maintenance. The next challenge that we will have is data quality and availability. The kind of data that we will get will be huge. It will be certain petabytes per day. To maintain the quality of the data in these cases is really difficult. We have to rely on certain high volume of data with high frequency, and the parameters that will be utilized for data quality should be significantly high and should be in real time. Generally, there'll be a lot of noisy and inconsistent data, which will lead to a lot of false positive cases. To learn about them, we have to go on a reinforcement learning shape, where based on the data set, we will learn new optimization technique and again implement it. So it will be a great, huge learning curve. It took us around 4 years to implement such a technology in our current company. Then there'll be complex implementation. You will need skilled personnel like data scientists, engineers. There'll be a lot of system integrations because we will have a lot of third parties. Different systems talk differently. To integrate with different systems will be a challenge. Then there'll be training of drivers and maintenance. The AI model, as mentioned earlier, will need a lot of validation to remain accurate. There will always be environment changes. Right now, we are talking about diesel vehicles. Future is coming is electric vehicles. So all these electric sensors that are today with this diesel vehicle should also work with the electric vehicles. That will bring significant challenges. So it will be an ever-changing work. Apart from the technology, today we are using one technology, maybe a Spark. Tomorrow it will be Flink. To evolve around with technology also a challenge in fleet management. You have to always be up to date. Cybersecurity risk. What will happen? Suppose your data gets hacked. What will happen if one of the sensors get hacked and turns wrong, which will send you wrong data? That will bring down my entire system, entire prediction system. That also requires robust security protocols to protect sensitive vehicles and operational data. Then there'll be scalability challenges. As we are dealing with petabytes of data, we need system that will support these petabytes of data. Ensuring real-time processing and storage at scale will be technically very, very demanding. False alarms. Overly sensitive models may trigger unnecessary maintenance and increasing cost. Imagine that my vehicle is sending wrong message that it is going to break down. I take that to a workshop and the salesman comes and says me, no, there is no issues with the vehicle. You get a wrong signal. That will incur significant cost. So we have to be very sure what kind of model we are bringing and what it will be predicting. Future scope. In the current state, there's still a lot of things that we can work to enhance this. We can add sensors in battery, voltage, ignition state, maybe at engine coolant level. Maybe we can add a sensor in odometer to see if it's functioning properly. We can put sensors in the speed so that the driver can maintain the speed. If he is going over speed at a certain signal, it can automatically control the vehicle and break it down so the driver can never go out of speed. Transmission of oil, if you are running low in oil, it can indicate the driver that you are running low on oil and route it to the nearest center where he can fill his vehicle. But imagine a battery vehicle driving on the road and the battery is low and the driver is unaware of that or driver ignores it. The vehicle will automatically send an alarm to the nearest operations center to ask the driver to route the vehicle to a nearest location where he can charge the vehicle. Otherwise, it will increase significant cost. So in a sense, this industry is evolving and there's still a lot of things to do. So that ends my presentation. I am open for any questions now.
Hi, Pratim. Apologies, there just seems to be a technical issue on my end where I can't hear you properly. Um, I'll ask the questions and hopefully we'll be able to figure it out from there. So I loved that presentation because it kind of showed the complexity of a lot of times people think, oh, this is kind of a fairly simple system. But when you showed all of the tooling and all of I loved as well the case studies that you gave of how you have to factor in if something gets hacked or if something, a faulty sensor. So can you go into a bit more detail? Because I'm not sure if I missed it or you explained, how do you, with your models, handle that situation where you might have like a faulty sensor or you might have a hack sensor? Because you said you have to care for that in your models to make sure it doesn't skew your output. But can you go into a bit more detail about how you actually do that?
Oh, it's a wonderful question, actually. Uh, a sensor generally sends me a throughput per second, which we capture in real time. So there are certain data points that we see. There are around 120 data points from a sensor when it comes to us and we read it. So a data point can send you a signal that, okay, my level of noise from this vehicle is at the threshold maybe at 16.1 level. I'm just making out the number. The next time it is sending me a signal that my threshold of noise of my sensor is at around at 14.1. That means within 1 millisecond, the noise attribution increase significantly. That's the reason it is sending me two void signals. At one time, we can say, okay, my vehicle deteriorated significantly, but we have a history algorithms which will go and check a similar pattern behavior of sensors which was faulted during a runtime, whether my current signal matches that frequency or it's beyond that threshold level, through which I can confirm, okay, whether my sensor is behaving properly or something is wrong in that. Then I need to dig deep and see what are the data points other sensors are sending. If other sensors are also sending different kind of data sets, which looks conflicting, I imagine that my vehicle data points are hacked by some third party for malicious content, and I can immediately disconnect that vehicle from my data set, from my Kafka topic, saving my algorithms to send distress signal to the operation center so that it will look like, yeah, all my vehicles are getting distorted with this noise. Hence the reason whenever I see this kind of predictions based on our threshold value and history machine learning algorithms, we will immediately disconnect that. Hope I answered your question.
Yep. Thanks. Sorry about the delay in my response. I'm listening on the live stream. So yeah, no, that's really complex. It's really interesting how you've gone then to the engineering level to figure that out. And just in other complexity, I love looking at your kind of, I guess, your system architecture, where you've got all the different levels. One thing I did notice is because the first thing was it scared me. It scared me how much was there. But the second one was when I was looking at the data stuff. For example, I saw Mongo and DynamoDB and Snowflake, and like there seemed to be a little bit of, I wouldn't necessarily say it's duplication, but were all of those points necessary? And why did you decide to kind of introduce different technologies where potentially you could have streamlined and used a single one?
Oh, it's a very good question, actually. Uh, when we talked about data, telemetry data, there's a huge volume of data. There are certain limitations where which data storage systems we will use. MongoDB generates very fast, so if I have to do some real-time predictions, that is best suited for it. DynamoDB is kindly for batches, although it is very fast, but whenever you are getting more than 150 throughputs per second from a Kafka topic, we have seen DynamoDB to slow down. Generally, we use that for batch predictions. Suppose something there which I can predict after a delay of 15 minutes, I generally use DynamoDB. But whenever there's a near real-time prediction, we send the data across to MongoDB, which will retrieve my data into my prediction into few seconds. For other storage system, whenever there is a delay, like I run batch jobs a week or maybe a day, because those are cost effective. To store data from a longer term perspective, I use them. So that's the reason you can see different data sets. It's kind of optimization between cost and what is required. If I create a large scale MongoDB system, it will be huge costly. It's expensive for the company. So we kind of done a permutation combination which system to use for that so that we can manage our cost as well.
Great. So it's kind of fitting your model with your kind of needs. That's great. Yeah, I think might just call it time there. So apologies for the technical difficulties. It's just quite difficult to listen and respond on this, but I believe it's on my end. So apologies for that. But I just want to thank you once again for sharing, because I thought that was really interesting, looking at it from the more technical side, because we hear so many talks about, oh, just integrate ChatGPT or AI into your systems. But I really love the example that you gave in the question as well about how do you make sure your model doesn't get polluted? How do you actually keep with all, as you were saying, that real-time processing if you can't keep up with the batch? Right? So I just want to thank you once again, Pratim, for sharing.
Thanks for the chance, and I appreciate giving me the opportunity to speak here. Hopefully, I will speak more here. Thank you.
Excellent. So that brings us to the end for today. I hope you enjoyed the talks that we had, and apologies about our technical difficulties. But if you like the concept of what UXDX is doing, we're bringing together product, UX design, and dev together to kind of share how they can improve together. So today, for example, we had a product-focused talk from Megha, and then a more technical-focused talk for Pratim. But it's unless you get everybody together, that's where the magic comes from, and that's where the products come from as well. So in USA next May, we'll have 40 speakers, 8 workshops, 500 attendees, and we'll be also doing a session in Berlin in May as well. So please do consider joining us for that. But if not, I just want to thank our speakers once again for sharing their amazing case studies, and I look forward to seeing you at the next UXDX Online. Thank you.